Next, we have a whole lot of rules of logs. Now, these rules need to be memorized in time. I'm going to name the rules and give some examples of how they are used. And then in the third part of this video sequence on logs, I will show how we are most likely going to be using these rules and properties of logs. Okay, so item 1. The log base b of b is equal to 1 because b raised to the power 1 is b and log is an exponent. Okay, item 2. The log for any base b, and the bases b are the same as the bases that we have in exponential functions, usually greater than 1, at any rate always greater than 0, and never equal to 1. Where was I? The log base b of 1 is 0 because b raised to the power 0 is equal to 1, and as we're just saying, log is an exponent. So I want to think of what exponent I put on b to give me a 1. That's 0. Okay. The log base b of b to the x is x because log is an exponent. Okay, now there's something else important happening here. We have a log function that has an exponential function inside. And remember that logs and exponents are inverses. That means that they collapse together, provided they have the same base, the log and exponential function, and poof, out comes the inside. So the reason for this is we have inverses. These are inverse functions, and whenever we have f of f inverse of x, we have, in effect, an identity function. Now, this works the other way around too. If we had f inverse of f of x, then we would have an identity function. So, specifically, this exponential function b raised to the power log b of x, these collapse together and squeeze out the x. So this is taking the exponential of a log function of x, like so. And this is because these are inverse functions. So the big take home from this one is that we can use log and exponential functions to make each other disappear. And when we make things disappear, we simplify our work. Maybe I should say simplify, not functions there, but expressions, two sides of an equation. That's what we're typically going to do. Other properties that we use to simplify, or in some cases complicate things, are these. If we have the log of a product, this is equal to the sum of the logs. So let's illustrate this with an example. Log base 2 of 32 is equal to the log base 2 of 4 times 8, because 4 times 8 is 32, which is equal to the log base 2, according to this rule, of 4 added to the log base 2 of 8. Okay, now we know that 32 is equal to 2 to the 5th, so we can say already, okay folks, the exponent here is 5. Well, the log base 2 of 4 is 2, and the log base 2 of 8 is 3, and son of a gun, we have 5 on both sides of this. If you have trouble remembering these, think of a simple example like this one. Okay, so we have a rule for the log of a product. And we also have a rule for the log of a sum. Not a sum, a quotient. So the log base b of this quotient is the difference of the logs. And we could do this the same way by taking, say, 32 over 8 and getting the log of 4 out of it. So let's do the log of 32 over 8. I want log base 2 of 32 over 8. That's equal to log base 2 of 4, which is 2. Well, according to the rule, this is the difference of the log base 32 and the log base 2 of 8, which we know is 5 minus 3, which again is 2. So we use this kind of operation to simplify or sometimes complicate other expressions. Okay. And then the last big one is this. Well, I suppose this is really just about all of them. We have the log base b of any expression raised to some power. I'll call that p. Well, because log is an exponent, I can bring this p down here, and this is equal to p times the log base b of x. So this is very helpful for getting exponents out of our way. Now, I need to backtrack a bit and mention some things that I forgot to mention before. As with exponentials, we have many different log functions. They all have the same shape. They all intersect at the point 1, 0, and we have a formula for changing from one log base to another. We might say that this one is log base 10 of x. This one could be log base e of x. This one could be log base 2 of x. Well, you have to reach a certain number, you have to raise 2 to a higher power. Then you have to raise 10. It happens that in general practice, 2 of these are commonly used. I use base 2 because it's important in computer science, but it isn't really important to anybody else. So 2 bases are commonly used. for logs. We have log base 10 of x, which is what they mean if you just see log with no particular base written there. This is called the common log. Then we have log base e of x, which is used so much that it is also known as the natural log of x. So this is not pronounced ln, it is pronounced natural log, or you could just say log. And depending on context, that'll be understood either to be base e or base 10. Well, these two are the only bases that you actually see in your calculator. So what I'd like to do is go back to an equation like this last one, where we bring down the power and show that the two of these give the same result. So here's the example that we're going to use. I want to show that the log base e, obviously, of 5 squared is equal to 2 times the log of 5. Okay, so now let's bring up the calculator and show that. Here it is. Okay, so here are my two log buttons. This doesn't say so, this is just log base 10. This doesn't say so, this is log base e. So we were looking at the log of 5 squared. So that would be the log of 25, wouldn't it? The log of 5 squared. It seems to know what I'm talking about, though I'm not sure that I do. Let's check that out by doing the inverse. I'm going to store that answer I just got in the variable x, and now look at e raised to that power x, and there we go. That's 25. So then the question is this log of 25 the same as 2 times the log of 5? Yes, it is. So the moral here is that we have managed to show that the log of 5 squared is the same if I bring the exponent down in front and call that 2 times the log of 5. So that's the end of our basic properties of logs. There are a lot of crazy examples that we could give, but I'm going to emphasize the important things today and get to some of the crazy maybe later this week.